Good morning, everyone. We are the Information Retrieval and Extraction team, and today we're here to present our project, Data Augmentation for Information Retrieval. Information retrieval is the process of querying a large amount of data, usually in the form of documents, and retrieving relevant answers for the query. It usually consists of two phases. The first phase where we identify relevant documents, and the second phase where we re-rank documents according to their relevance. One of the most widely used techniques for information retrieval is BM25, but it is a bag of words model that relies heavily on word overlap. And therefore, if there's a mismatch between documents and queries, it does not perform as well. And the other way to do information retrieval is using representational neural networks. And this is able to express the problem much better. However, neural networks require a large amount of data to avoid overfitting. And in a real world scenario, the amount of data available is highly limited. And this is the exact problem that we are trying to solve through our project. So we are going to apply data augmentation to handle scenarios where there is limited data. So the first method that we're using is first group of methods that we do is rule-based augmentation, with methods such as random word insertion, random character deletion, and so on. And we also work, the other technique that we're using is model-based augmentation. This is applied at a query level as well as at a document level. And the methods that we dealing with here are scent augment and in-parse, which we'll be discussing in detail in the next few slides. We hypothesize that rule-based augmentation techniques can lead to an improvement in the information retrieval pipeline. Model-based augmentation techniques can also lead to an improvement. And finally, a combination of the rule-based and model-based techniques applied at both the query and document level can lead to an overall improvement in the retrieval pipeline. The major features that we will be discussing and what as part of our project is rule-based augmentation techniques, which are broadly grouped into three different categories of character level, word level, and document level. Model-based augmentation techniques. Here, like I mentioned before, we use in-parse and scent augment. In-parse has new query generation and non-relevant document generation, and scent augment is used to generate similar queries to a given query. And finally, we'll be interfacing this with and integrating this with FlexNewArt. So the intended users for our product are researchers, businesses, newcomers in NLP who can incorporate all of our various options that are available by using the pluggable data augmentation module. The module that we built is contains multiple data augmentations and query reformulation techniques. It is made up of simple rule-based as well as model-based techniques. So when there is data entering the information retrieval framework, in the data processing phase, we have the data augmentation module that can be plugged in. It contains both rule-based and model-based techniques. And this data after processing is sent to the re-ranking model. So we develop and support for integration into existing IR frameworks, with our current focus being on FlexNewArt.
Hi everyone. So I'll be talking about the bigger picture of like where the DA module actually fits in the IR pipeline. So here you can see that the general IR pipeline is such that you have a query and a document collection. The query gets passed through a retriever, you get a ranked list, and it passes through a re-ranker, and then finally you get a re-ranked list. But what we plan to do is insert our DA module in between the retriever and re-ranker so that we are able to fine-tune the re-ranker. This is the implementation overview. Like Ramya said before, we will have rule-based and model-based techniques for our DA module. So let's talk about the low-level design. The way that our DA module fits in the FlexNewArt framework is using data augmentation classes as wrappers and a config file. Now, the config file will contain parameters such as the augmentation probability and whether we want to perform the augmentation on queries, documents, or both, and so on. So the config file is passed to the data augmentation wrapper. The wrapper in turn passes the query or document to each particular technique according to what's been selected by the user. And we implement all this using a factory design pattern, so such that the augmentation registry is able to register each technique as a class using decorators in Python. And finally, the each data augmentation technique class will implement augment, which will have the specific details of how the method is actually implemented.
Having discussed the low-level design, let's look at some of the non-functional requirements. The first one that we offer is interoperability, where the library can be easily integrated with pre-existing frameworks. We write our code in a very modular and encapsulated in function manner so that you can easily unit test it. The code is robust and well documented, and without looking at any code details, it can be plugged into any other IR framework. And we make sure that the data augmentation does not become a bottleneck in the training pipeline. The resources that are involved here are the data sets, MS Marco and Orcus, which were procured and pre-processed. The hardware that we've used is basically for training BERT-based rankers, GPU with G4D and XLarge, and approximately 19,000 resource hours of AWS GPUs for experimental ablations, and for storing the model checkpoints, EBS and EFS-based storage. We also conducted an extensive literature survey of all the data augmentation and reformulation techniques to identify our baseline and our technique. The assumptions that we go with is that the data set follows Heap's law and Zipf's law, which are corpus level statistics. And also applying a data technique will retain the true labels in the newly augmented documents. We have constraints on the amount of resources that we have available. So we do not consider models that have high computational costs as well as large data sets. The system environment is a Python-based environment. We make the system open source and portable on all machines. And finally, we have a pip installable pluggable module, which is a data augmentation library. And it contains multiple data augmentation techniques, which can be applied at the document and the query level.
Hi, so let's talk about data design now. So firstly, the primary data set that we'll be using is the MS Marco passage ranking, which is used for training purposes. But we also use another data set called Orcus, but this is just used to find similar queries. And we can see this in the data flow diagram as well, that the MS Marco passage collection is used, like the query and document are passed through a retriever, our data augmentation module, as well as re-ranker, whereas the Orcus data collection is only used to find similar queries in the data augmentation phase. So let's talk about the specific techniques now, the first one being rule-based. Let's say we have a sentence, so we can perform word level augmentations on it, character level, as well as synonym and hyponym replacement. And the hypothesis here is that the word level techniques are helpful in redistributing the words. The character level techniques are useful in mitigating any effects of typos, and the synonym and hyponym replacement increase the vocabulary so that we can cover up the vocabulary gap problem. Then finally, we have our first model-based technique called query reformulation. But here the query is not augmented in the general sense. We actually replace the query using a similar query. We have two pipelines that we use using a FIAS index and a Lucene index. So in the FIAS pipeline, the query is encoded using a multi-QA distilled BERT, and it is it retrieves similar queries using a FIAS index. Now, FIAS is a library that is used for clustering of dense vectors, and it is used for very fast, efficient retrieval of similar queries. And it generates, later we generate a ranked list, and then finally we create a query cache so that during training time, the DA module is able to fetch similar queries very quickly from the cache. The Lucene pipeline is quite similar, the only difference being that the retriever uses BM25, and also the index is Lucene, which is a bit slower compared to the FIAS fast retrieval. And we generate a rank list here, but we also re-rank it using sentence BERT so that the queries the final queries that we use are better than the previous ones. And we finally create a query cache out of it as well. And all this acts as augmented data for our like DA pipeline.
Hi, everyone. So the next model-based technique that we talk about is in-parse. In-parse is a query generation technique which uses few-shot learning to generate synthetic queries given a document or a passage. The authors of the paper had used OpenAI's GPT-3 for these query generation and training the model. We have adapted this into our MS Marco pipeline by using open source language models from Hugging Face like GPT Neo and Bloom. So how we have incorporated this into our pipeline is explained with this diagram. So given the documents and the queries, the query generation module will have a language model from Hugging Face, and given the document, it generates queries from this. These generated queries along with the documents give us the positive pairs, and then we use these generated queries along with the corpus of documents and incorporate it in BM25 to give us non-relevant documents, which give us the generated negative pairs. And this together gives us the augmented data. The hypothesis is that training the re-ranker using these additional queries which will give us a better performance. We build these rule-based and model-based techniques by deploying a model with these major features. So it will be a pluggable module which is compatible and integrable into FlexNew and other IR frameworks. We have used configurable parameters for our augmentation experiments so that new users can easily modify these parameters for their new experimentations. And we have also provided the functionality to combine different techniques and while making sure that they are also independent and don't depend on other modules. Next, the tools and dependencies that we have used for our module is that we have used Python 3.8 for our development, and we have integrated everything to the FlexNew framework. We have used the MS Marco and Orcus datasets as explained before. We have also referred to codes from this list of GitHub repositories for the different augmentation modules that were explained before. And we have used the NLTK toolkit for the synonym and hypernym word replacement techniques in our rule-based augmentation. However, there are some risks and challenges that are involved with these augmentation techniques that were discussed. So the first one is that sometimes the rule-based augmentation techniques may change the meaning of the query as explained in this example. So it may not find the similar query or document once these are replaced. Next, there are a large number of hyperparameters involved in our augmentations, like the different probabilities at the different stages of the augmentation, like the probability of choosing the probability of augmentation and the harshness of the augmentation. And the parameter set that we choose can significantly improve or decrease the performance, and it is important to find this, but it's actually difficult given the large number of variables. Also, the user who is choosing these augmentation techniques should have some domain-specific knowledge, because for specialized domains, sometimes all augmentation techniques may not work. Next, we come to the test design. So since we have a large number of augmentation techniques, it is very time-consuming to actually evaluate it on multiple seeds and iterations and tune hyperparameters for a large validation set. So we have broken down our experimental methodology as follows. So first, we try experimenting with each augmentation technique individually, such as the rule-based augmentation techniques and the query reformulation techniques. For in-parse, we have tried out two different training methods. One, by mixing the original and the synthetic data and training it together. And the second way we adopted was that to consider the original and the synthetic data set as separate sets, and using a pre-training fine-tuning approach by pre-training on one set and fine-tuning on the other. We used a small validation set of 100 queries from the MS Marco train set for the hyperparameter tuning of the rule-based augmentation techniques. Once we tune these hyperparameters and choose the best performing models, we actually try out a combination of multiple techniques. So for example, we pre-train on the in-parse synthetic data and then fine-tune it on a mixture of rule-based augmentation techniques on the original data. This has been evaluated on the larger validation set of 1,000 queries, and we analyze these results. Finally, our ultimate results will be reported on the original MS Markov validation set, which we are considering as our test set. The result significance was tested using a two-tailed t-test. And these are some of the experimental components. So the framework that we incorporated everything into was FlexNewArt. The retriever was BM25. The re-ranker was Ernie. And we evaluated everything on mean reciprocal rank, which is the mean of the reciprocal of the ranks of the predicted answers.
Once we completed running the experiment, these were all the results that we had. So for the rule-based techniques over here, our experimental setup was with a training set size of 1,000, a validation set size of 1,000. The validation set size was kept consistent throughout experiments to kind of do a proper comparison across them. We ran it with 3 seeds to account for variability and for 4 epochs. The metric that we used was mean reciprocal rank. Over here, we've also measured the significance of the results using a two-tailed t-test. The significance asterisk marks are denoted as follows. 1 asterisk mark indicates a p-value less than 0.05, 2 asterisks indicate a p-value less than 0.01, and 3 asterisks indicate a p-value of less than 0.001. Over here, we noticed that a couple of techniques do perform better than the baseline. However, only 2 of them are significantly performing better than the baseline. Also, we noticed that the techniques that perform well at document level do not necessarily perform well at query level or vice versa. However, we do notice that there are 2 techniques that perform consistently slightly better, but it's not significant when we look at the results across both document level and query level. The next set of experiments we ran were for query reformulation. This is one of our model-based techniques. In this case, again, we had a training set size of 1,000 with a validation set size of 1,000. We ran it with 3 seeds and 4 epochs. The same metric was used. Over here, we had 2 different techniques. As mentioned earlier, we had the FIAS retrieval and leucine retrieval. Both of them do not show any improvement in performance over here. The next model-based technique that we were using was InParse. Now, InParse is a technique used to generate synthetic data. So we kind of wanted to see how well we were able to replicate the paper before we applied it to our experimental situation. So the original paper used GPT-3 for data generation and Mono T5 for re-ranking. However, GPT-3 is pretty expensive to use, and Mono T5 is a pretty large model. So they did have a really good performance. We tried to replicate it with something that would be more accessible. So we used Bloom, which is both of the models that we have are kind of open source and available. We used Bloom for generating the data, and to re-rank it, we used a much smaller model, Diverta, over here. And we saw pretty much a similar performance, though it's not as good, but it did show us that our technique was working as expected. So now we applied to again, coming back to the same experimental setup we have. Over here, we generate the synthetic data. We generate a synthetic data of training set size 10,000. And we have 4 experiments listed over here. The first one is the baseline that we talked about earlier, where we're just training it with the original data. The second one is basically training it only with the synthetic data generated using InParse. No original data is involved at all. We noticed that given that no data was used at all over here to train the model from the original set, it does perform pretty well in the validation set. The next thing that we try out is a combination. So we tried 2 combinations. The first is pre-training on the synthetic data and then fine-tuning with the original data. Over here, we observe a slight improvement in performance. And the second experiment that we try out is training it with the original data and then fine-tuning it with the synthetic data. When we fine-tune with the synthetic data, we fine-tune for just 1 epoch because this size is really large compared to the original data. We notice a slight improvement in performance for the last 2 techniques over here. However, none of them are significant. So next, we our initial hypotheses were that maybe the techniques alone might give us a smaller performance improvement, or they might lead to not a significant performance improvement, but a combination of the techniques might leverage different domains and kind of different ideas and lead to a better performance improvement. So the first combination that we try out over here is combining a rule-based technique with a model-based technique. So the rule-based techniques are listed over here, and we use the in-pairs as our model-based technique over here. The way in which the experiment is set up is that we first pre-train it with in-pairs data, and then we fine-tune it with the original data using the respective rule-based technique over here. We do notice much better results than when we talked about only rule-based experiments. Over here, a lot more experiments are significantly improving over the baseline. Additionally, we observe significance across both document level and query level. The next thing that we try to do is, given the positive results we had before, the next thing we try is combining two model-based techniques. So over here, we do something pretty similar. We use a pre-trained in-pairs model, which has been trained on the synthetic data, and then we fine-tune it using the query reformulation techniques. We noticed that using fast retrieval with in-pairs results in a significant improvement in performance. The next thing that we try to do is pretty interesting. Up until now, we were using original data, except for the in-pairs baseline that we saw where we were only using synthetic data. We thought that we could try a combination of techniques also, where we were not using any original data again. So over here, we're only using synthetic data. We do the fine-tune, we do the pre-training using the in-pairs 10,000 synthetic data. And over here, when we're fine-tuning, instead of using the query reformulation technique on the original data, we use it on the synthetic data itself. So at this point, everything is just synthetic data, and we're not introducing any sort of original data. We do observe that it is not competitive with the baseline, but given that there is no data involved over here at all, it does perform relatively well on the validation set.
So up until now, we have been mostly talking about the quantitative aspects of the results that we gain when we use data augmentation with information retrieval. So we do believe that there's another side of this coin, and there is qualitative results to be found when we talk about data augmentation. So to test this hypothesis, we come up with robustness analysis of the models that we train. So what we do is we take the initial validation set that we had used for testing the previous models and add certain level of noise to it. So we basically try to do it in two settings, in a low noise and in a high noise setting. So in the low noise setting, we add noise to 50% of the documents or queries with a probability of 0.1. And in the high noise setting, we do that with a probability of 0.35. So basically we have four sets, one where we just corrupt the documents and with low and high noises, and then the others where we just corrupt the queries with low and high noise. And what we observe that in the document side of things, when we do it for the documents in the low noise setting, a few of the models hold up, but the results are much better when we introduce more and more noise. And similarly, when we move to the query side of things, we see that the results are much more better, as most of the models do perform well compared to the baseline. So across both these experiments, we see that all the models suffer in some drop of performance, but that drop is significantly lower when we talk about the models that were trained with data augmentation. And yeah, so that's all for it. And so overall, we did a lot of experiments and we tried out multiple techniques. So if we had to summarize everything in a single slide, what we would say is we started off with a baseline that gave us a mean reciprocal rank of 0.2740. We tried two types of techniques that were parallel to each other. That is rule-based techniques, where one of the techniques, random word insert, did perform well and outperform the baseline. Similarly, just using model-based techniques, also we were able to outperform the baseline. And finally, to sum it all up, what we say is that more is always better, as the more amount of techniques and data that we add, we keep improving performance. As combining all these techniques together, we were able to significantly outperform the baseline as we get a result of a mean reciprocal rank of 0.2926. So moving forward to the discussions and the future work. So starting off with augmentation performance, again, as we repeatedly have discussed, that the performance gains that we see through augmentation is highly dependent upon the hyperparameters. We have done extensive experimentation that has allowed us to find some values that work well, but the transfer of these values to other data sets cannot be commented upon. And applying these same augmentation techniques with the same effectiveness on other data sets might need significant hyperparameter search again. Then coming on to the robustness analysis, we do see that training models with data augmentation, in some cases, even if it does not lead to significant improve in quantitative performance, it does make the model more robust. And also another observation that came out of here was that query side robustness is more when queries are augmented during training, which kind of stays in line with a general search engine scenario where we would expect queries to have more variability as compared to the documents, because the document set is mostly fixed and it's the queries that change on a day-to-day basis. And so although we see that on the document side, the robustness thing is not very consistent, but it can be explained by the fact that while creating the data set, we add noises of different types, and we can further try to test it by adding specific types of noises and then seeing how the model holds up. And the most interesting thing that we believe that came out of this project was to train only on synthetic data. Again, the results were not as good as the baseline, but given the fact that we basically did not use any of the original queries that were present in the data set, we do believe that it has significant promise in the future. One of the things that we can see, we have not yet experimented with different types of models to generate the data, along with the combination of the encoder that we used to index and retrieve from the Orcus data set. And this could be a low-hanging fruit that we can test in the future that would help us gain more understanding of how well this method works. And coming on to the reflection part, this project gave us a really interesting time to have worked with information retrieval systems and gain hands-on experience on training, tuning, and analyzing models. We also had the opportunity to work on an open source framework, FlexNuart, which helped us improve our software engineering skills. Moreover, having to work in a resource-constrained environment, we were able to improve our how we design experiments and streamline our understanding of the problem so that we don't waste resources. And with significant emphasis on both improving the model performance along with the considerations of open world deployment helped us make better design decisions. And finally, this was our fall plan that we wanted to do. So we have achieved almost everything that we had planned for, with the report being due next week, and we'll be finishing that. So these are the main terminologies and the acronyms that we were using throughout the presentation. And these are the changes to the previous deliverables that we had, references, and thank you. And we are open for any questions.
Thanks, guys. Okay. So let me take a look at my notes here. So you guys had well-structured slides, and I think you started your presentation with sort of a good overview of kind of what you were going to talk about. But I think you could have spent a little more time with background. So you could have sort of said what FlexNuart actually was, you know, before you started mentioning that you were going to use it. But given that the majority of your audience is me and Leo, you know, for this presentation, that's kind of okay. But if you were going to use these slides to like make a presentation to like a prospective employer or somebody who's not in this space, you would probably want to spend a little more time in the beginning talking about what is IR, what are the steps in IR, how do we measure, you know, the results of an IR system, why is data augmentation important, you know, what is the state of the art, and then what are we drawing on, you know, literature. I was able to keep up okay, but I was thinking, you know, that if I had a non-IR person watching this, they would have been at a loss there. I realized that since your time is limited for this presentation, you have to pick and choose and present the most important stuff. I think it's great work. I think it's, you know, good results. But I don't want you to walk out of here thinking that there's, you know, no way to improve this, because you could have put more, you know, as the overview part. So I think if you do talk about your project, you know, when you're being interviewed, it might be a good idea for you all to kind of put together a few, you know, overview slides for newbies to go along with this. I sort of figured out what augment prob was. It's the, sort of roll of the dice that decides whether you augment an element. When you do that, do you keep both the original and the augmented data element, or do you completely replace the data element? Okay, so n doesn't change. Okay.
Again, like that original one again.
Oh, so it's possible that I could see both of them.
Yes.
Okay, very good. Okay, but it's the size of the overall sample size is the same in each run.
Yes.
Yeah. Okay, great. So the non-functional requirements, they were nicely presented, but they were kind of necessarily abstract in the sense that it's sort of hard to measure a real, goal in some concrete way there. Just be aware of that, because a lot of, sort of picky software engineering people will say that you should try to quantify, your non-functional requirements, because otherwise they're not testable. So did we meet the maintainable goal? No, how do you measure it? So you mentioned that there were some constraints that prevented you from working on larger data. And we all understand that that's important when you are exploring techniques and you want to do as many experiments as possible in a limited amount of time. But there is a possible risk there, which is that you've constrained yourself into a space where what you're doing is sort of leaving out highly relevant domains or data sets. So do you think there was any risk in what you chose there?
Like restricting ourselves just to MS Marco, we could have probably used another data set to validate our results as well. But given kind of the computational limitations already here, we were not able to do it. We're kind of focusing on being able to at least run the validation for the two MS Marco data sets, so that we can like claim that when it's working, it's not just a random chance, because we have explored a huge space and we don't want it to be just something.
Good. Well, yeah, and I think exploring a large space with 1,000 is great. And now, when you have the stuff that seems to be working well, you can take your time to, test it on bigger data. Okay. You mentioned that there was variance in the performance of specific techniques on the query versus the document level, but you didn't explain why. To me, as somebody that's worked in this domain, that's a perfectly reasonable thing for me to hear, but can you tell me why that seems to be the case?
It's just like a lot of times it's really restricted, so we didn't something that we have been not that harsh at a document level, have been augmentation was not as pressure at the level, resulting in a difference in performance across the two of them. We tried to account for that by lowering the threshold for price, but that does still kind of leave that keep that question open as to how much low is low enough. And given the restricted amount of determinate switches is there, we pick the lowest one that should be used.
Right. So the idea would be that if I had some normalized Levenstein distance, which was smoothed by the size of the text, then it would be obvious why queries are more highly effective. Okay, great. So in-parse and the rule-based approaches complemented each other in a way that allowed you to get a significant result. Why is that? How do they complement each other? Do you have any intuitions about that?
One of the things that we could think of is that in-parse data was generated using a large language model. So it does not actually perfectly reflect a real-world scenario. So that's because our data was in a smartphone, that is again taken from the big search logs. So it is kind of, it replicates what is being seen in the real world, and the other in-parse data is not very replicative of it. So that's where when we add these augmentations that try to replicate what a search engine is in the real world, so that's
okay. And then presumably that's true because of the distribution of phenomena in the test set. Okay. Good. So you talked about getting real world software engineering experience. Did you actually make commits to Flex New Art that are now out in the wild? Okay. Okay, good. So let's hopefully get that all the way through there. Very good. Okay. Leo, do you have any questions for the team? Oh, I see. Yeah, you have some comments. Yeah, please take the floor. Are you muted, Leo?
Yeah, sorry, actually I got disconnected just a few seconds ago. So I hope you don't mind if I make a couple of comments.
Oh, please do.
Yeah, well, first of all, thanks a lot. I'm really happy about what was achieved, and I could potentially make a couple of minor comments, but I would like to comment more on the significance of the work. So first of all, in the NLP general NLP domain, there is a lot of work on data augmentation, and generally it's shown to be useful. I am not sure I know at least one study of data augmentation techniques for IR, except for these like recent model-based approaches. That some of, and we can see, well, see why. Apparently it's much harder to make them work, so you need to be more careful in what techniques you choose. So I'm really happy that you folks like spend time tuning hyperparameters, and we now know which techniques can work and which we should try first. So that's really important. And second, these recent model-based approaches, like based on prompting, there are really like three papers, like two practical, sort of semi-practical papers that were published, but they're not really practical. The InParse paper is using 3 billion parameter model. Good luck with that to use in production. And they also use GPT, which is kind of somewhat expensive. You would, if you generate say like hundreds of thousands synthetic queries, it is going to be something like thousands of dollars possibly. So it's and so it's always nice that you can and we get good results now with like sort of off-the-shelf resources, not exactly for free, but much cheaper. And there was also a scientific question that we don't know, like when we use GPT, and there is a Google paper that's using an even bigger model, internal. We don't know how these models were trained. So why do they acquire these capabilities to generate queries that are feasible, like usable in information retrieval domain? Is it something related to training? Do they train on some kind of data and just don't tell you? I don't trust these corporations. I don't know what they did, but I do trust authors who trained the Blue model, and I know that there was nothing special. I can be like highly confident that it was trained as described. It was a group of scientists, so that we can reproduce with the open source model. That's an indicator that these models with scale and more data and next token prediction training somehow still acquire these information retrieval capabilities. And we didn't observe that with smaller models. So there are these emerging IR capabilities. And I think it's answers also an important scientific question.
So Leo, let me ask you, should the students be, trying to wrap up a publication now? Or does it make more sense to do deeper experimentation before going for a paper? Because I can imagine this turning into something more like a really comprehensive, journal article over time. But what's your advice for the team?
So we had that conversation. Yeah, that's a really appropriate question. So we had this conversation in the one thing that the team should probably do, just add a few more of like what I call validation experiments. Take these models and evaluate it on 3 query sets: full MS Marco development set, and there are 2, and that's given that the model is already there. They just compute the number, statistical significance, and they have the all preliminary experiments. And that, I think, I thought we would exclude parse from this, but actually now I think we should like take it as is and try to package as a workshop paper. It's going to be difficult to make a more comprehensive paper with just a single collection, but for a workshop paper, I think it's going to be just great with all the robustness analysis. But also was another thing that I was more like personally involved with, replicating the original in-parse data, and also a sort of combination of in-parse and the follow-up Google paper. And for this, I have preliminary results, and it would be really nice if we can ship it as a CGIAR reproducibility paper, because we basically, what I see so far, we basically reproduce that in-parse paper and sometimes even get better results using not using GPT-3 and using much smaller models.
Yeah, that's another whole angle that I find pretty fascinating.
Yeah,
on
and
this whole
yeah,
thing. So that's a good idea too. So we're going to have to give up the room, but
Yeah.
let's continue the discussion. And Leo, you and I should probably get a meeting to talk about, continuing new topics and continuing topics for next year.
oh yeah, absolutely. Yeah, thank you everybody.
All right, thanks, Leo. Take care.
Bye bye.